In this section, we will develop a LMS adaptive filter to clean up a noisy sinusoid. Let's get started. So firstly, we will define the signal parameters. So we start off with a sampling rate of 1000 Hertz, and the sampling time is 1 by S rate. Duration of the signal is 2 seconds. Frequency of the signal is 1 Hertz. So we define the time axis, which is starting from 0 seconds and will go up to the duration, that is 2 seconds. And in 2 seconds, there will be 2000 samples. So that is given by duration multiplied by sampling rate. So this is our time vector. This defines our time axis. So now let's generate the clean sinusoidal signal. Let's call it signal, and it's a sine signal. So we have frequency available to us, we have time axis available to us, and pi is a constant, and we multiply by 2, and we generate a pure sinusoid. Once this signal has been generated, we are going to mix it with noise. That noise is of the same length as the signal. So here is the noise vector. Actually, it's a Gaussian noise with the mean 0 and standard deviation 0.5, and it's of the same number of samples as the signal, that is 2000 samples here. And then we take this noise and we add it with the signal to generate our noisy signal. So here we are, till now we have been able to successfully generate the noisy signal, and from now on we are just going to implement the LMS filter. So initially let's initiate the filter parameters. So let the learning rate, that is mu, be 0.01, and we are going to be designing a 32 tap filter. So there will be 32 coefficients in the filter, and initially we initialize all these filters to 0. So all the weights are initialized to 0. We have 32 filter taps, so all these 32 are initialized to 0. And let's also have a placeholder to store the output of the filter. So since the input to the filter is 2000 samples of input signal, noisy sinusoid, the output will also be 2000 samples of the filtered signal. So, and all of them are initialized to zeros as of now. And then we again initialize two variables, two arrays, to store the mean square error before filtering and mean square error after filtering, to see how much of the improvement has taken place once the LMS filter has been implemented. So in this part of the code, what we are going to do is we are basically calculating what is the mean square error before the signal enters the filter. So what we are doing is that we are taking, so this step is basically defining the window of the filter, which is 32. And then we are going to take slices of the noisy signal, 32 slices, and the desired signal, which is our 2 sinusoid here signal. And then I'm going to subtract my desired signal from my noisy signal, which will result in the error or the noise. And then I'm going to take the square of that error and then mean of it, which will result in the mean square error at the input of the filter. And I'm going to store that error in the array that I've initialized here. And I'm going to loop through this entire for loop for till the time my signal samples are run out. Now we implement the LMS algorithm. So in this, again, we have to initialize a window which is commensurating with the number of filter taps, that is 32. So my index is moving from 32 to the end of the signal, which is 2000. And then I'm going to extract the noisy signal over these 32 filters, 32 taps. And then this particular code is going to flip the signal. So if you remember, in convolution, we need to flip either the kernel or the input signal. So firstly, I have extracted the noisy signal, 32 samples of it out of 2000. And then this part of the code flips this signal. And to generate the filter output, we use this X, which is a flipped version of the original noisy signal. And I take a dot product between the weights and the X. So these two lines are essentially implementing convolution. I could have done it in a straightforward manner by using a function called n3.convolve, but I wanted to show that convolution is nothing, but it's just a dot product where one of the signals is flipped. So once we have found out the output of the filter, then we need to calculate the error. So the error is the true signal minus the filter output. So this is what is the error or the noise. And then we are going to take this error and take a square of it to make it squared error, and then mean of it. So now this is the error at the output of the filter, mean square error at the output of the filter. And then we are going to calculate the gradient and update the weights. So gradient is calculated in LMS using this formula, -2 multiplied by the learning rate multiplied by the error output, which is here, and into the X. And then once this gradient is calculated, we are going to update the weight by subtracting the gradient from the previous weight. So this entire loop is implementing the LMS algorithm. Once that has been implemented, I'm going to calculate signal to noise ratios at the input and output of the filter. So for that, I need to first calculate the signal power. My signal power is straightforward. I just take the signal, I square it, and I take a mean of it. That's the definition, classical definition of power of a signal, square of the amplitude. And then I'm going to calculate the noise power at the input of the filter. So essentially, I take my noisy signal, which also has the signal power, clean signal power in it, and I subtracted the clean signal power from it. So what I'm left with only is noise, and then I take that noise and square it and calculate the mean of it. So this becomes my noise power at the input of the filter. I also need to calculate noise power at the output of my filter. So output of my filter is filter out, and from this I subtract the signal power. So I get and square it and then take a mean of it. So I get the noise power at the output of the filter. These are required for calculating the signal to noise ratios. So SNR at the input of the filter is nothing but the signal power divided by noise power. So signal power was calculated here, noise power was calculated here. I just take a ratio of it and then take a 10 log of this ratio. That will give me SNR at the input of the filter. And at the output of the filter, I'm going to take signal power divided by the noise power at the output, whatever noise that has remained after filtering. So that will give me the SNR at the output. And then I'm going to print out these various parameters and make a plot of various signals. So let me just run this code. Pretty straightforward code. Here we are. So firstly, the SNR of the noisy signal at the filter input is 3 dB. So you can, the first plot is that of the noisy signal as well as the filtered signal as well as the original signal. So if you see this plot, the x-axis is time. So we had time duration up to 2 seconds, and y-axis is amplitude. My original signal is in green. I'm not sure if you're able to see it here. This green signal is the original sinusoid, and then it got corrupted with the noise. So the blue signal is the noisy sinusoid, and then the dashed orange is the filter output. Now as you can see that this orange line is very closely tracking the original signal in spite of so much of noise which is riding on top of it. So filter has been performing pretty well. In the second plot, I have, this is a plot of mean square errors. And what I have done here is that on the x-axis I have time, and on the y-axis I have mean square errors. And this blue is the mean square error or the noise at the input of the filter. So as you can see, this noise is pretty substantial. The mean square error is quite high. And once we filter the signal, the noise, as you can see from the orange plot, it becomes quite less. And this orange plot shows that. And you can see that the mean square error of the output is very low. One interesting thing happens at these points. Here the error tends to increase, and let's investigate why. Basically, if you see that this is happening somewhere close to 0.5, 1, etc. So what is happening here is that the original signal is zero crossing at this point. And since the zero crossing power of a signal is very low and the noise riding on top of it is very high, the LMS filter starts to track the noise instead of the original signal or the true signal. And that's why for a moment it tracks the noise, and once the zero crossing is over and the original signal gains its strength or the amplitude, then LMS filter again catches up with the original signal. And as a result, at every zero crossing, if you see, there's an increase in noise, and then after that it's a decrease in noise. So you can, and then we let's have a look at the SNR. So pretty clear that this blue signal has got very high amount of noise. Actually speaking, it is 3 dB. And once we filter out this noise, our signal to noise ratio improves to 22 dB. And that's happening because of this LMS filter. Also, please note that initially this filter takes some time to converge. And that is natural because the filter weights are adapting. So this portion, you will find that the filter is not able to track. And once the filter weights have converged, then the filter starts tracking the sinusoid. Now we can play around with various parameters of this filter. For example, we can increase the noise, let's say 1, and see if the filter is able to track. So as you can see, the noise has increased. The SNR at the input of filter has decreased to -3 dB, but the filter is still able to function fine, and it's able to track the signal, track the sinusoid, though now the perturbations are quite high, and still the output of the filter is giving a SNR of 15 dB, which is very, very good. We can also change the learning rate. Let's see if this has an impact. So you see that this orange portion here, it initially fails to track the signal because the filter is still converging, and the reason for that is that the step size or the learning size or the learning rate is too small, so filter takes some time to converge and then it starts tracking the signal. As far as signal SNR improvement is concerned, it has not been much. So let's go back to our original learning rate and let's see what happens if we increase the filter taps. If we go for a 64 tap filter, let's see what happens. Oh, so filter has failed to converge here. So 64 tap is not working. Let's say 48 tap filter. And as you can see, the 48 tap filter is also not performing very well. You can see huge amount of noise here, especially at the zero crossing, which is actually at this point. So for this particular noise statistics, a 32 tap filter is ideally suited and is working pretty well. We're back to 32 and you can see that the improvement is almost 18 dB plus. The core of the filter is essentially this gradient tracking, which has come from LMS algorithm, and this gradient is basically adapting the weights of the filter in accordance with the noise characteristics. I hope you have learned something. Thank you for watching.